So let's look at an example of moment of inertia by integration. Let's calculate Ix and Iy for this function right here, this red function, as it goes between 0 and 1 on the x. The function is y equals 2 times the square root of x. Okay. Now, I'm not writing any of my units, any of my work. All these units would be in inches or, we're going to say these are inches. I usually don't put my units. I keep everything in consistent units when I do this and at the front, and then I just kind of don't write my units the rest of the time until I get to the end, just because it can get messy because you're doing big integrals and everything anyway. So I'm just saying here, all units are in inches. Calculate Ix and Iy. So we're going to do this Ix first, and we're going to do it two ways. We're going to use both a vertical and a horizontal element just to show you the two different versions. And then we'll do Iy, much more, I'll pick the one that I like better. So option 1, we're going to use a vertical element to solve for I sub x. So this is my first element here. It's dx wide by y tall. The centroid of this is at y over 2. So what I was saying before, if we're finding the moment of inertia about the x-axis, wouldn't this thing also have its own moment of inertia about this axis right here? So we would have to incorporate an AD squared term. However, there is an n. Remember, I told you that most of these tables talk about, for rectangles, they do bh cubed over 12, and then for about its bottom edge, bh cubed over 3. So I can just use this formula and integrate it, and that actually will be the moment of inertia of a rectangle about this bottom edge, which happens to be the x-axis. So that's what I'm going to do for this. I'm going to need, since it's a definite integral, I need limits of integration, and since I'm integrating with respect to x, I'm going to use my x limits, and that's 0 and 1. So our lower is 0, our upper is 1. So the moment of inertia of a rectangle about its bottom edge is bh cubed over 3. What's my b? Well, it's dx. What's my h? It's y. What's y equal to? 2 times the square root of x, or 2 times x to the 1/2. So now I can integrate this. So I have the moment of inertia is equal to b times h cubed over 3. And it's a definite integral going from 0 to 1. I will cube my 2 and get 8, and I'll factor out the 8 and the 3. So I'll pull them out of the integral, and now I'm just integrating x to the 1/2 power cubed times dx. So this is really still just that h cubed, and that's the b from this formula right here. So if I integrate that, I get 8/3 2/5 times x to the 5/2. So just doing simple integration. And then I'm going to plug in my limits, which are 1 and 0. So those are pretty simple limits, right? Because I can just plug in 1 here. So 1 to the 5/2 is just 1. And then the 0 bit at the end, just for formality, I'm showing it. It all is 0. So anyway, I evaluate this, and I get 1.07 inches to the 4th is my I sub x. So the moment of inertia of all this about the x-axis is 1.07 inches to the 4th. Let's do the same example now, except for using a horizontal element. So here's my horizontal element. Its height is dy. What's its width? That's a little tricky, right? You could say x, but you'd be wrong. X is this value over here, right? Because x comma y, the coordinate of the function, is that value, is right along this red line. So if that's x, and this here is 1, then this value here is 1 minus x, right? All right, so the integral that we're going to use now is the more fundamental integral for moment of inertia. It's that y squared d8 integrated over the area. And we are using a horizontal element. So we need to do a little work to get everything set up right for our integrals. The width of the element, as I mentioned, is 1 minus x. We need everything in terms of y, though. So instead of y equals 2 times the root of x, we need to rearrange that. And we will get x is equal to 1/4 y squared by just dividing by 2 and squaring to get x, right? X is equal to 1/4 y squared. That makes 1 minus x, the width of this element, equal to 1 minus 1/4 y squared. As we are integrating with respect to y, we need to know the y limits of integration. So we're not going to use 0 and 1 anymore. What we need to do is we're still going to have 0 as our lower limit, but we need to figure out what the y value is right here. How do we figure out what this y value is? Pretty obvious. You plug in your x here. So 2 times the square root of 1 is going to be 2. So our upper limit is quite simply 2. So now I'm going to integrate. My integral between 0 and 2 of y squared dA. So 0 to 2, y squared, and then dA, this area here, is 1 minus x times dy, right? So there's dA, and that is more formally called, because remember 1 minus x is the same as 1 minus 1/4 y squared. I need everything in terms of y. So my integral from 0 to 2 of y squared times the quantity 1 minus y squared over 4 times dy. Multiply my y squareds through, I get y squared minus 1/4 y to the 4th dy, and then I integrate, and I get 1/3 y cubed minus 1/20 y to the 5th, and I evaluate that between my limits of integration of 2 and 0. Plugging in those limits, I get 1.07 inches to the 4th. Same answer. Again, the horizontal element here, you can see it's a little bit more problematic about where it's occurring. It's still pretty simple, though. The main thing is, for me, being able to rearrange that function easily in terms of, to get it to be x equals. If you can't do that very easily, then I would stick with that vertical element. Just my advice. So let's look at I sub y now, just to make sure that we're cool with this, because that one was y squared dA. Now we're going to do x squared dA. This is now our perpendicular distance to this differential area. So we're going to square x, multiply it by dA. It's all very similar. So here, I think I'm going to go back to my vertical element again. So now I have that integral of x squared dA. I can use that version of the formula again, because I have dx wide, y tall. My x limits will be, since I'm integrating with respect to x, it'll be 0 and 1 again. So let's integrate. So x squared dA. So I have x is just x, right? And then dA is dx times y, where y is 2 times the root of x. So, my integral of x squared dA turns out to be the integral of x squared y dx, because y dx is dA. And then I have that form being further reduced down to the integral of x squared times 2 times the square root of x dx. Simplify that, pull the 2 out. 2 times the integral of x to the 5/2 dx. Perform the integration. I get this evaluated between my limits of 0 and 1, and I get 0.571 inches to the 4th.